We'll kick off with Dan Freeman from Kurita. And I'm actually looking forward to this quite a bit, cracking the code, some CSI-style presentation. So yeah, Dan, we're looking forward to this. Thanks.
Okay. Thanks, Derek. Hello, everyone. My name's Dan Freeman. I am the product manager for Kurita's membrane treatment chemical solutions. My job is to manage the product line, to be a technical contact for our sales team, and also attended functions like this to demonstrate some of our products. Today, I'm going to talk through a few case studies, actually more than one case study. I'm going to go through a series of case studies whereby I will demonstrate some of the benefits of our approach to membrane systems, how we tackle problems that we see on membrane systems, and use the information that we develop to provide solutions for our customers. So, okay, reverse osmosis. It's been around for a long time. It's a process that we have seen for more than 40 years now. It's the dominant process for desalination. It's extremely widespread use in industry, and it's also increasingly used in wastewater treatment. The main issue, or the thing that you need to be careful of when operating these systems is, of course, maintaining the condition of the membranes. And we know that when you get water on the membranes, there's always the potential for either contamination, accumulation of materials on the membrane surface, things that can damage the membrane. And when you accumulate materials on the membrane surface, you have the potential for issues with the operation. In particular, things like having to clean regularly, which means consumption of water. We're having energy issues. If you accumulate materials on the membrane surface, it becomes less efficient. You have the potential for damage of the membrane, a permanent performance loss because of particular foulants, and all of these things can contribute to CO2 contribution in terms of CO2 usage, and of course they all cost money. So these are all issues that we need to be aware of. Having said that, all these things come in with the feed water. It's obvious that when we see a problem on an RO system, we need to work back through the system and understand where and why the problem occurs. So we go through a particular process. It's an investigative process. We want to understand each element of the system. We want to understand what's performing well and where we can improve the system, either in terms of a chemical change, a dose rate change, maybe in some cases just a change in the operation in order to improve the system. It's an investigative approach. And what I'm going to do today is talk about one of the tools we have in our locker for understanding what issues an operator may have with their particular system. I'm going to talk about autopsies and how we use an autopsy in order to identify issues with the system and correct those issues. An autopsy is an approach where we take an element that's fouled or damaged in some way, we break it open, we take a look at the membrane surface, and we can make an understand what is the best. In fact, is the best way to really understand what's going on with the membrane. We can see exactly what's on the surface. We can see quite a lot of the history of the membrane from an autopsy. We can also see if there are multiple issues. And in fact, most cases, I would say, there is more than one issue with an RO membrane when we break it open and have a look. And you can see what exactly is there. One of the most useful techniques that we have in the autopsy is what we call chromatic elemental imaging. So you can see the colorful image there in the center of the screen. That's a kind of technique, an advanced technique similar to SEM microscopy, where we can look at the membrane surface and understand the distribution of elements across the surface. And that tells us a lot more, it gives us a lot more information in terms of what's on the membrane surface and how it's deposited. If you use a standard SEM image, it's a black and white image, it can tell you what elements are there usually, but we can't understand exactly how they're distributed. So one of the real benefits of that process is to understand how those are distributed. And in some cases, you can see different layers of distribution. So you can understand that there's been more than one event that's caused a problem. So what I'm going to do today then is go through a few of our autopsies, take a few cases from our list of autopsies and sort of explain how we go through this process and some of the benefits of it. Okay, so the first case then, it only takes a few minutes to look at the cartridge filters here to see what sort of issue we might be facing with this kind of system. And this extreme case where you can see that we have accumulation in the UF, we have accumulation on the cartridge filters, and then accumulation of material on the feed face of one of the membranes. When we open one of those membranes up, this is what we are seeing. And if you know anything about, if you've seen this kind of problem before, you even from the color, you're gonna have a good idea that this is going to be an iron problem. Iron problems are pretty common. And you can see that also when we take a look at the CEI image, we have iron present, but we also have a lot of calcium. Iron and calcium carbonate scale often precipitate as in common because the iron will actually deactivate the antiscalant. So if you have a lot of iron in the feed water and you don't account for that in your dose rate of the antiscalant, then you will often see that you see not only the iron precipitate, but calcium carbonate also. And that's what's happened in this case. This is a schematic of the system that this element came from. It's a well water source, and it's typical for a well water to have iron present as ferrous ions, soluble iron. And that's not a problem for the RO, actually. It's only when you bring it to the surface and it gets oxidized that iron can be a problem in terms of oxides of iron, ferric hydroxide, and these things that accumulate on the membrane surface. In this particular scheme, what the operator is trying to do is oxidize all of the iron that comes up with the water, give it enough residence time so that it precipitates, and then remove it with the ultrafiltration system. Obviously, when we looked at the ultrafiltration system, you can see that already it's pretty overloaded with iron. And so this system wasn't working. Basically, there's not enough residence time for the permanganate to oxidize the iron and remove all of it because it's passing through the system to the RO. And even if it does, the ultrafiltration system is struggling to cope with the amount of iron that's present. So what was the solution to this case? In fact, what they did in this case was to bypass nearly all the pre-treatment for the RO. Okay, and the idea here is that if you keep the iron in the soluble form as ferrous iron rather than ferric, then it will pass through the membrane system without precipitating. Okay, and it's not an issue for the antiscalant. So that's what they actually did in this system. The issue that you have to be very careful of when you're applying this kind of system is that if the iron oxidizes at the membrane surface, it will damage the membrane. There are intermediates in the process, in the oxidation process, free radicals, that will damage the membrane. So if we attempt to do this kind of process, bypassing the pre-treatment, we have to make sure that there is genuinely an anaerobic environment that passes all the way through the system. In terms of the cleaning of the membranes in the system, iron is a relatively easy material to remove. So in this case, we have a particular cleaner that's very effective at removing iron. So we're able to recover the membranes in the system, and by making this change to the situation to the pre-treatment, this system runs well. That's kind of an example of that. So this is our second case. This is a pretty unusual case. You don't see this kind of thing very often. But this is a case where the actual shell of the RO system, or the RO membranes in the system, has been damaged. And it's the result of using a very, very aggressive cleaner at a very high temperature. This kind of cleaner is it's designed for silica removal. The operator believed they had a silica problem on their plant. The system wasn't running well, poor performance. And so they assumed it was silica, and they cleaned with this aggressive cleaner. And this is a pretty extreme case. You don't see this sort of thing very often, but of course, a high pH, very aggressive cleaner, and it's actually damaged the shell of the element. This is what that element looks like when you break it open, and you can see that, ironically enough, there is no real silica challenge in this membrane. So they used the wrong cleaner in any case. It wasn't the right cleaner for this particular problem. And I think that's something that you have to, the real benefit of an autopsy, of an investigative process, is to understand exactly what the problem is and to target to target the problem with the right solution. And of course, in this case, not doing that has led to an issue. This kind of foulant, again, is iron, manganese, and calcium carbonate, particular problems. These things we can clean up. We were able to clean this system up pretty well. This is a CI image from a different system, but had a similar problem. So on the right-hand side, you can see there's a dye test where we can see dye has passed through the membrane, and we can see that as an indication of damage. This element was damaged. When we actually look at the CEI, we can see that there are traces of calcium fluoride on the membrane surface. Calcium fluoride was not something that you would expect to see from the water analysis. It's actually a trace of the cleaner. So again, this is the same sort of cleaner. It's damaged the membrane, and it's left some traces. And you often see other things, other cleaners can cause, you can see on the CEI also. Sometimes you see where citric acid has been used for removing scale. Calcium citrate is not particularly soluble. So if you don't control the pH well when using citric acid, you can see that there's more of a problem. You actually precipitate a scale during the cleaning process. That's something else that we see quite often on the CEI. You wouldn't expect to see calcium citrate on a membrane surface. Also, there are certain limits in terms of what you can use in terms of surfactants. Many commonly used surfactants are a problem for RO membranes. So if you use the wrong cleaner, you can usually pick these things up on the CEI. The pre-treatment for the system that I showed earlier on with the damaged membrane elements was also a problem in terms of the same sorts of failures. And you can see here, these are the fibers for the UF fibers. We are able to recover those elements too. You often see with the UF fibers that material accumulates at the top and bottom of the bundle, because there's less agitation in the backwash and if there's an air scour. So you get an accumulation of these materials at the ends of the modules. If you can use a more formulated cleaner, which is more effective, you can get a better clean with that than you would generally expect to get with sodium hydroxide, for example, or an acid. In this case, we used a formulated cleaner, and we can see a big improvement in the performance of the module. Okay, when we see a membrane like this, it's pretty often the case that you have no chance of recovering something that's been as badly fouled as that. It doesn't mean to say that the element can't be of use. Okay, so we understand that there's a problem. We know that there's a precipitation or an accumulation issue on the membrane surface. We're going to throw this membrane away anyway. It's not going to be something we can recover, but let's open it up and take a look and see what the problem is inside. And here you can see very clearly that this is a scale issue, it's calcium sulfate scale. We cannot recover that element, but it tells us a couple of things. It tells us there's an issue with the antiscalant, or there has been an issue with the antiscalant, because if you're using the correct antiscalant, you shouldn't see scale form. it tells us what we need to do to clean whatever elements are still recoverable in the system. So we know now we can select a cleaner for that particular challenge. So even though that membrane's lost, we can still make use of the information that it tells us for that element, for that system. Okay, here's another case for a UF system. This is a UF that was not being recovered well with the current regime. They didn't understand exactly what the problem was. We were just using generic chemicals, and we took a look at the membrane. We looked under the microscope. We did a CEI of the surface, and we can see that there's a fairly mixed kind of deposit on the membrane surface. When you have a mixed deposit like this, we've got clays, we've got silica, we've got iron, we've got usually there's quite often organics on the membrane surface. When you get a mixed matrix like that, it can be very difficult with traditional solutions to get the membrane clean. So in this case, we used a proprietary liquid cleaner to remove the metals and the silicates, and improved a big improvement in the performance of the system. So we're going from 124% improvement in the flux of the system. This is another case where we looked at the membrane surface. This is a brand new system, not been in operation very long, and it's on a well. And what happened is the well wasn't well stabilized before they started up the system, and they were using drilling muds in order to drill the well. And what happened is they've contaminated the membrane on startup with material that's come directly from drilling the well. And that's a case of, getting the membranes cleaned up, and then making sure that the wells run and stabilize before we actually start pushing for the RO. You can see there's a lot of silicate, aluminosilicates in this case. Cleaning it up with this kind of material, we can clean up with a proprietary cleaner. The idea here is to disperse what's on the membrane surface rather than dissolve generally. And in this case, we were able to make a very good recovery. You can see the cells in the center there. That's an actual piece of membrane taken from the element. We do a sort of test clean in the lab, and you can see that the performance of the cleaner visually, it's a very nice example, this, because it's a very visual result of an important clean. This is another system from a well, actually, another CI from a well system. Again, you can see unusual contaminants here. These contaminants have come from the process upstream when they've drilled the well. So we've got titanium, which is a very unusual thing to see on most membranes, and other issues. Again, we were able to clean this particular system up with a proprietary cleaner. Okay, this is another situation that we see quite regularly, whereby you don't necessarily see a single problem on the membrane. Okay, in this case, we've got two different scales. We've got silica scale and we've got calcium carbonate scale. Now, those two scales require different treatments in order to recover the membrane. So we need to approach those two different problems in a different way in terms of cleaning. And once we can see what the issue is on the membrane surface, then obviously we have a better chance of cleaning the system up. And again, you can see we're able to recover this particular system very visually again with the cell tests. This is a UF system. It had a very, very, very low flux. But when we opened up the membrane module and looked at the membranes, there was not that much there to see. And it looked like, given the performance of the membrane, we were expecting much more material on the membrane surface. When we looked at the CEI, though, you can see that there is a very uniform, consistent layer of material on the membrane surface. And the primary failant in this case was barium sulfate. Barium sulfate is something that is relatively easy to clean off if you use the right cleaner. And we were able to recover this membrane. You can see an improvement, 818% improvement in the permeability after cleaning this membrane. So you can see how poor it was before we started and how we were actually able to recover this particular system. So just knowing exactly what's on the surface of the membrane is really valuable. To stop a lot of you can spend a lot of time trying different things to try and recover a system, but actually taking a membrane out, looking at what's there, seeing what you're doing a test in the lab, see which is the best cleaner. Sometimes when you have multiple failants, it's actually the order that you apply different cleaners that's as important as anything. So it's like taking a membrane out and actually doing those experiments in the lab can be really valuable in terms of recovering the system. This is the last example, and this is sort of contrast to the previous one. It's very clear that we have a problem on these membranes. You can see there's a lot of material on the membrane surface. Again, very poor flux, but by applying two cleaners in combination, we're able to address the issues here. The primary issue again is iron, also some silicates, although it's not so clear on this CEI. But again, we're able to recover the system, and we know what we need to do. Once we've done this autopsy, once we've looked at the membrane surface, we know what we are looking to do. Okay, so that's a small example of some of the autopsies that we have conducted. And we do about 350 autopsies a year in our global laboratories. That experience is where we get the basis of understanding what chemicals we need to apply. Also, when we're developing new chemicals, when we're looking for new solutions, it's a great database for us to be able to understand what challenges people are looking for, are facing with different waters. And it's really the basis of our experience comes from a lot of those autopsies that we're performing. Once we've done those autopsies and we go through our process of tests, we can usually recover most systems. There are occasions where there's something there that's very, very difficult to recover, and maybe it's particularly if the failant's too ingrained, then it can be difficult. But mostly everything comes off, and we're able to recover systems. And that basis of targeting the right cleaner for the right problem is really what this is about. Okay. I'll leave it there. I've got 3 minutes left, so there's enough time for a few questions. Anyone got any question?
Yeah, thank you. That was cool. I've never seen those surface pictures like that with color and
yeah,
really, really interesting. Just a quick one. You showed that one of the images was that gypsum scaling on an RO, a calcium sulfate scale on an RO membrane.
Mm-hmm.
Have you also looked at, gypsum is a big issue in mine water in South Africa in particular, and a lot of the mine water plants are operating high recovery with anti-scalants, and then trying to precipitate the gypsum out of the brine,
Mm-hmm.
and then managing that in multiple
Mm-hmm.
processes, and in some cases going to thermal evaporators for the brine stream. Do you have experience with managing the precipitation of gypsum in thermal evaporator systems? Not so much so it's not an RO question.
It's a stairstream question. I don't actually, but that's something that would be interested to talk to you about, because I mean, really, that's a solution. If there are issues there, that's kind of our modus operandi, to go and see what the issue is and try and find a solution. And obviously, we have a lot of experience with that scopes, not just in membrane situations, but in cooling towers and so forth. It's one of our key technologies. So I mean, managing that sort of. But when you say managing, what's the function of the evaporator? It's presumably to completely remove the water, or is
correct? So these are approaching ZLD water systems, and ultimately trying to get all the water out of the brine stream that is generated in an RO.
So you're actually trying to precipitate the scale in that case.
It's a long conversation, but I'm just not aware of anti-scalant chemistry that's applied in these thermal systems. I'm interested to see if you have that experience. Yeah.
Okay. Anyone else?
Thank you for that insightful presentation. I just have a question with that one where you change the order, where you say you have a membrane first, and then you take care of the iron afterwards. Are you not precipitating the iron afterwards? Where you said you are going to, you first have the RO system, and then you say you take care of the iron afterwards.
Okay.
So you
Further downstream,
you
yes, that's
solve that yeah.
that's a potential
So
problem.
you follow those So basically, do a toxicity test to find out if you apply that to the environment, if it's okay.
Yeah, I mean, in that case, that's the system that was in the US. I'm not sure what actually was happening after downstream of the RO system. Obviously, I'm focused on the membrane system, but yes, that's going to be a problem at some point further downstream. And how they manage that, I can't tell you, to be honest, at this moment in time. If you're interested, I can look into it though. But yeah.
And with regards to the membrane itself, do you also focus on particulate fouling, or you just looked into scaling and biofouling?
Any kind of failing on the membrane.
Any kind of foul, so you can use those chemicals and.
Yeah, we've got a range of different cleaners, so and they're targeted. So we're looking for things that will actually address each individual issue. I mean, they all have a reasonable profile against more than one potential problem, but there will be usually one where it's particularly useful. So we have one that's particularly good for metal ions. We have a cleaners that are particularly good for silica. We have cleaners that are particularly good for biofilm, depending on what the issue is. Yeah.
Okay, thank you.
Okay.
Thank you for the presentation. Very interesting. Any experience on oil-fouled membranes?
Yeah, oil can be a problem. We have cleaners that can address it to an extent, usually. But depends on how much oil is there and exactly what kind of material it is. We have cleaned up some elements with specific cleaners, yeah. So it's something that we would, if you have a problem, in that case, it's definitely worth looking at an autopsy, and we can try different things and different solutions. Trying to do that on site is a difficult thing. You know, we would need to know a little bit more about the problem.
Yeah, thank you.